Today, let's design a chat cache and stop a cache stampede. Picture one popular conversation. Its recent history key expires just as a cache node fails. Thousands of reconnecting devices ask for the same page. If every miss reaches durable storage, a normal cache expiry turns into an origin outage. The cache is supposed to remove load. In this moment, it multiplies load. Our interview exercise assumes 10 million daily users, 1 million live connections, and peaks of 250,000 history reads per second. We need a truthful answer even when the cache is cold and the message store is slow. This is an illustrative interview design, not Databricks production architecture. First, separate the message truth from the speed layer. A send enters the chat gateway with a client message ID. One conversation owner assigns the next stable sequence, commits the message once, and only then returns a durable acknowledgement. A durable event fans that committed message to connected participants. Reconnecting devices recover from their last durable cursor. The message store is authoritative. The cache is disposable. A cache loss may make reads slower, but it can never lose an acknowledged message, create a new message, or reorder the conversation. At the assumed peak, the write path handles 100,000 sends per second. Cache work stays off that commit boundary. That keeps a healthy send near the exercise's 300 millisecond P95 target, even when history caching is unhealthy. Now choose what the cache may remember. Use a partitioned distributed cache for recent conversation metadata and closed immutable history pages. One illustrative page key is history conversation 4290. It contains messages 90 through 99 and a watermark that says truth through sequence 99. A metadata key such as head conversation 42 carries the latest committed sequence, say 109. The history service authorizes the participant before it trusts either key. Closed pages never change, so they are safe to reuse. The open tail is either read from durable storage or cached under a versioned key with a short lifetime. We never silently mutate an old page beneath the same key. That watermark is the contract. It tells a reconnecting client exactly how far this response proves the conversation history. Partition keys by a stable hash of the conversation ID. That keeps one conversation's metadata and adjacent pages easy to locate. Give each shard replicas so a single cache node failure does not erase every nearby copy. But consistent hashing does not solve a hot conversation. One famous thread can still overwhelm its shard. So the history service adds per key request coalescing, tenant budgets, and a tiny bounded local result window. Capacity is protected by quotas and eviction policy, not by hoping traffic is uniform. For an ordinary hit, the service reads one page, checks its watermark, and returns it. The target is 150 milliseconds at P95. For a cold key, the service may read durable storage, build the page once, and publish it with a jittered time to live so neighboring hotkeys do not all expire together. Return to our expired hotkey. The first request becomes the fill leader. It acquires a short lease for that exact key and spends one origin read budget token. Requests arriving behind it do not start their own database queries. They join the same in-flight promise, wait within a firm deadline, or leave with an explicit retry response. When the leader reads messages 90 through 99, it verifies the page boundary and watermark, fills the cache, and wakes the followers. 10,000 cache misses become one origin read, and 10,000 shared results. The lease needs an expiry and a generation number. If the leader dies, a new leader can take over. If the old leader returns late, its stale generation cannot overwrite the newer fill. Request coalescing saves one process. The lease protects the key across processes. Now make the message store slow. This is where truthful degradation matters. Each shard has a small origin concurrency budget, a queue limit, and a deadline. When that budget is full, new fills do not pile up forever. The service applies back pressure and trips a circuit breaker before the message store collapses. If an authorized closed page is still available from a replica or a stale cache entry, the service may return it with its original watermark and a clear stale indicator. That page is immutable. We are delaying newer history, not inventing history. Mutable head metadata does not get the same permission. If no safe page exists, return a degraded or retriable result. Do not replace missing messages with an empty page. A short negative cache is allowed only for a page proven beyond the authoritative head watermark, and it expires quickly. Fast, stale but truthful, or explicitly unavailable. Never fast and fictional. When a cache node fails, the hash ring routes reads to a replica or the next owner. Existing fill leases expire safely, and durable storage remains the source of truth. Rebuild from observed demand, not from a full scan. Rate limit warmup per shard. Keep the origin concurrency budget in place. Add time to live jitter and promote the hottest closed pages first. That prevents recovery itself from becoming another Stampede. Watch 4 signals: cache hit rate, requests collapsed per fill, origin saturation, and degraded responses. Lease contention and late fill rejections reveal hotkeys or failing owners before users report missing history. The trade-off is real. Coalescing, leases, replicas, and watermarks add operational complexity. We accept that complexity only because the cache remains disposable, and every returned page still carries a verifiable boundary. Here is the design to remember. Durable storage owns ordered messages. The cache stores recent metadata and immutable pages with sequence watermarks. A history hit is fast. A miss enters one coalescer. One leaseholder reads the origin. Followers share that fill instead of multiplying it. When the origin slows, budgets and backpressure contain the damage. A safe, immutable page may be served with its watermark. Otherwise, the system says retry. When a cache node fails, replicas and demand-driven warmup rebuild capacity without touching message correctness. One expired key should create one fill, not 10,000 database reads. That is how a chat cache stays fast without ever pretending it is the truth. Practice the complete Databricks chat cache interview exercise on FastPrep.